Hey everyone, welcome back. Let's talk about another easy problem on Leetcode today, Fibonacci Numbers, Leetcode 509. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. The Fibonacci numbers, commonly denoted by Fn, form a sequence called the Fibonacci sequence, such that each number is a sum of the two preceding ones, starting from the numbers 0 and 1. That is, for numbers 0 and 1, f0 is equal to 0 and f1 is equal to 1. And for n greater than equal to 2, fn is equal to f of n minus 1 plus f of n minus 2. This sequence was first described by Indian mathematician Pingala in the 2nd century BC in the context of Sanskrit prosody and was later popularized in Europe by Leonardo of Pisa, that is Fibonacci, in the 13th century. And our task is to calculate f of n given n. Then in example 1, for n equal to 2, f of 2 will be f of 1 plus f of 0, and f of 1 and 0 are 1 and 0 respectively, so f of 2 will be equal to 1. Similarly, for n equal to 3, f of 3 is equal to f of 2 plus f of 1, and we have already calculated f of 2 in example 1, which was equal to 1, so our output will be equal to 2. Similarly, for n equal to 4, f of 4 will be equal to f of 3 plus f of 2, and we have already calculated f of 3 and f of 2 in example 2 and 1 respectively, which will be equal to 2 plus 1 equal to 3, and so on. Now, this is a straightforward problem, but it provides a perfect opportunity to introduce dynamic programming concepts. To start with, let's explore the naive approach first for calculating nth Fibonacci number, which is purely based on its definition, where f of n is equal to f of n minus 1 plus f of n minus 2. Let's solve it and visualize the recursion tree for n equal to 5. So we have to calculate f of 5, which will be sum of f of 4 and f of 3. But we don't have the value of f of 4 and f of 3. So we go down further to calculate these values. So f of 4 will be equal to f of 3 plus f of 2. Note that we have the redundant calculations. As you can see, we are calculating f of 3 twice. Then we evaluate f of 3, which will be sum of f of 2 and f of 1. And then f of 2 will be sum of f of 1 and 0. And now we have reached the base case, and we know the values of f of 1 and f of 0, which are defined as 1 and 0 respectively. So f of 1 is 1 and f of 0 is 0. So f of 2 will be equal to 1. Then f of 1 is equal to 1. So f of 3 will be equal to 2. Now for this f of 2, we will have a similar recursion tree like this one. But we can see that f of 2 will be equal to 1. So I will be just reusing this value for now. But in reality, we will have the recursion tree drawn somewhere below. So f of 4 will be equal to 3. And then f of 3, we have already calculated here, but there will be a recursion tree below it, and the value will be equal to 2. So f of 5 will be equal to 5. Here is the quick code for recursive approach with Java code on left and Python on right. First, we have a base case, that is, if n is equal to 0 or n is equal to 1, in that case, we will return the n itself. But otherwise, if n is greater than or equal to 2, then we compute the Fibonacci number recursively, where the method calls itself twice, once for the result of f of n minus 1 and once for f of n minus 2, and sum of the results. Here is a detailed recursion tree for n equal to 5. The time complexity of this approach is O of 2 to the power of n, because as you can see, this method generates a recursion tree with approximately 2 to the power of n computations to calculate the nth Fibonacci number. For example, if n is equal to 6, the recursion tree adds one more level compared to n equal to 5, and number of computations approximately doubles at each level. Hence, the time complexity will be O of 2 to the power of n, which is exponential. And the space complexity will be O of n, as the space is required for the recursion stack, which is proportional to the depth of the recursion, which is equal to n. Hence, the space complexity will be O of n. Now, while the implementation of the naive recursive approach is simple and directly follows the Fibonacci definition, it suffers from redundant calculations. As we can see, even for smaller n equal to 5, certain Fibonacci numbers like f of 3 and f of 2 are calculated multiple times. For example, f of 3 is calculated twice, f of 2 is calculated thrice. These are called overlapping subproblems, which occur when the problem can be broken down into smaller subproblems that are used multiple times throughout computation. Here, each result, such as f of 3 or f of 2, is needed multiple times during computation of higher level Fibonacci numbers, like for f of 5. Also, the results of the subproblems, for example, f of n-1 and f of n-2, are combined directly to solve the original problem, which is f of n. This gives the optimal substructure to the problem. And whenever we have overlapping subproblems and optimal substructures, this tells us that we can use dynamic programming here. Now we can solve this problem using top-down dynamic programming or the bottom-up one. And we can start with the easiest one, which is top-down dynamic programming, which uses memoization. Memoization is a technique where we store the results of the subproblems to avoid redundant calculations. It is like caching the result so that we can reuse it in other parts of the problem. So in the top-down approach, we start solving the problem recursively from the highest level. For example, here we start with n equal to 5. And then we save the results of the subproblems like f of 3 and f of 2 in a data structure like an array or dictionary. And when we encounter the same subproblem like for example f of 3 and we have already calculated it and stored it in the memo, we can reuse the saved result rather than recomputing it. So it is very close to recursion, but it caches the result so that we don't recompute it again and again. For example, for n equal to 5, initially memo will be empty. Now we calculate f of 5 as f of 4 plus f of 3, and to compute f of 4, we will compute f of 3 and f of 2, and again f of 3 is computed as f of 2 plus f of 1, and eventually f of 2 is computed as f of 1 plus f of 0, and now we have reached the base case, and we know the values of f of 1 and f of 0, which are defined as 1 and 0 respectively. So now f of 2 can be computed as 1 plus 0 equal to 1, which we can save in the memo table. So if we use dictionary, the key will be 2 and value will be equal to the result we have just calculated, that is 1. Or we can also use an array where we will store the result for 2 at index 2 with value as 1. So for simplicity, let's use the array. Now we can compute f of 3, which is sum of f of 2 plus f of 1, which we compute as 2 and store it in the memo. Now we have to solve for f of 4, but before that we calculate f of 2, which is already calculated as it is present in the memo table with value equal to 1. So we calculate f of 4 as 2 plus 1 equal to 3. So we save it in the memo. And now we have to solve for f of 5. But before that we should calculate f of 3, which is already calculated as it is present in the memo table with value equal to 2. So f of 5 will be sum of f of 4 plus f of 3, which is equal to 3 plus 2 equal to 5, which we will return as our answer. Now the time complexity of this recursive approach with memoization reduces from O of 2 to the power of n to O of n, since every Fibonacci number is computed exactly once. And the space complexity will still be O of n because of the depth of the recursion and this memo table that we are using. Here is a quick code walkthrough using dynamic programming with top-down approach with Java code on left and Python on right. Here, first we create a memoization array or list of size n plus 1 filled with all zeros initially. Now this code logic is very similar to recursive approach where we first check for the base case, that is whether n is equal to 0 or 1. In that case, we will return n itself. Otherwise, we will check if we have already calculated the value for n to avoid redundant computations. So if the value at nth index in the memo table is not 0, then we will return that value. Otherwise, we will compute f of n by recursively calling the helper function, add the results and store it in the memo table for the reuse later. And in the end, we will return the nth Fibonacci number as our answer. Now let's solve this problem using bottom-up dynamic programming approach. Because this method avoids recursion overhead related to function calls and minimizes space spent on the recursion stack. Also, for this problem, arriving at the bottom-up approach is quite intuitive. In this approach, we use tabulation, which involves solving all smaller subproblems first and storing their results in a structured table or an array, many a times called DP table. So for this problem, let's create a DP table of size n plus 1. Since the sequence starts with 0, now in this approach, we start solving from the smallest subproblem. So we already know the values for f of 0 and f of 1, which are 0 and 1 respectively. These values are stored directly in the array as the initial base cases. Now, using the results of the smaller subproblems, we can compute larger subproblems systematically, moving sequentially from f of 0 to f of n. So we iterate from I equal to 2 all the way up till 5 to calculate Fibonacci number for f5. So for I equal to 2, f of 2 will be calculated as f of 1 plus f of 0, which is 1 plus 0 equal to 1. Similarly, for I equal to 3, we can calculate f of 3 as f of 2 plus f of 1, which will be equal to 2. So if you observe carefully, we are solving the problem for the current number using the sum of previous two numbers. So for the ith number in this dp table, we can write it as dp of I is equal to dp of I minus 1 plus dp of I minus 2. And this is what we call dp recurrence relation. Continuing with I equal to 4, we get sum as f of 3 plus f of 2, which is equal to 3. And finally, f of 5 will be equal to f of 4 plus f of 3, which is equal to 5. And now, since we have filled in the last element, we can return it as our answer. Now the time complexity of this approach is O of n. Since we calculate each Fibonacci number exactly once, and the space complexity will be O of n because we are using this dp array of size n plus 1 to store intermediate Fibonacci values. Here is a quick code walkthrough of the bottom-up dynamic programming approach using tabulation with Java code on left and Python on right. Here again we check for base case, where if n is equal to 0 or 1, we return n itself. Note that we don't have to explicitly check for base case because they will be covered in the dp array initialization, but they help in improving the readability. Now let's create dp array of size n plus 1 to store the Fibonacci numbers. Let's initialize the base cases, that is dp0 and 1 to 0 and 1 respectively. Now we can iteratively fill the dp array by running the iteration from I equal to 2 to n using the recurrence formula, which is dp of I is equal to dp of I minus 1 plus dp of I minus 2. And once we are done with all the numbers, we will return dp of n as our answer. And now the question is, can we do better? And the answer is yes, at least in terms of space complexity. For calculating any Fibonacci number, we only need two previous values rather than storing the entire sequence. For example, to compute f of 2, we simply need to sum up 0 and 1. Similarly, to compute f of 3, we need to sum up 1 and 1, which is equal to 2. So at this point, to calculate f of 3, we don't need f of 0 anymore. So we can discard it and save space by just maintaining two variables to store the last two values. Let's call them previous 1 and previous 2. So now we can calculate f of 3 as sum of previous two values, which is equal to 1 plus 1 equal to 2. Similarly, we can calculate f of 4 as sum of previous two values, which is equal to 3. And finally, f of 5 will be sum of previous two values again, which is equal to 2 plus 3 equal to 5. And now that we have reached the value of n equal to 5, we will return 5 as our answer. Now the time complexity of this approach is still O of n due to sequential calculations. However, the space complexity reduces to O of 1 because we are just using these two variables. Here is the quick code walkthrough of the algorithm we just covered with Java code on left and Python on right. We again start with the base case, that is, we check if n is equal to 0 or 1. In that case, we will return n itself. Now we will initialize the variables previous 1 and previous 2 to 0 and 1 respectively, corresponding to values f0 and f1. These variables represent the last two computed Fibonacci numbers. Let's also initialize answer to 0. Now we will iterate from I equal to 2 up to n and calculate the current Fibonacci number, that is answer as the sum of two previous numbers, which is previous 1 and previous 2, and update previous 1 to the value of previous 2 and previous 2 to the newly calculated answer. And once the loop completes, answer contains the value of f of n, which is returned as the final result. And again the question is, can we do better? And the answer is yes, we can, using matrix exponentiation, using which we can compute Fibonacci numbers in O of log n time. This approach is particularly useful when dealing with larger values of n, where the linear solution might become inefficient. In this method, we use the following matrix and raise this matrix to the power of n and return the value in the cell at 0th row and column as the final answer. Another way to compute Fibonacci number is to use Binet's formula, which achieves O of one-time complexity. However, since Binet's formula involves irrational numbers, it is not typically used in programming due to precision-related issues. And both of these methods are very mathematical, and for programming purposes, we are now covered thanks to dynamic programming. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.